Okay, Year 11s, I'm going to do exercise 9F conditional probability today. So these are the questions I've set: 1, 4, 5, 6, 9, 10, 11, 12, 15, and 16. And those are the questions I'm going through today as well. So let's have a look at the first one. Question 1, it says, suppose that a fair die is rolled. Okay, fair die meaning you've got 6 sides. Okay, you've got a 6-sided die that looks kind of like this. All right. The event A, so the first thing that happens, or the set of A, which is defined by rolling a 6. So you only want to get a 6. So I'm going to write it out. Set A has the curly brackets 6. That's my only item in there. And event B, we've got rolling a number greater than 2. So numbers that are greater than 2, you can have 3, 4, 5, and 6. Yeah, so remember when you're rolling a dice, I don't know if this is what it looks like, but let's say the entire universal set of rolling a dice is 1, 2, 3, 4, 5, and 6. Those are the only possible options you can get. Well, then event A, which is the set, group A has 6, group B has 3, 4, 5, and 6, because we want it to be greater than 2. Now the question asks probability, or find the probability of A given that B had occurred. Okay, now when I answer this question, I'm thinking, all right, B is what apparently has happened first. So they already told me I've already rolled a number greater than 2, because that's part B. B has already occurred first. So if you think about it logically, what numbers that could I have that is already greater than 2? I could potentially have 3, 4, 5, or 6. Now out of these, what's the chances, because that's what they're asking, find the probability, the chances out of these numbers, what's the chances of getting A? Now, group A is just 6. So how many 6s are there out of these? Well, technically, if you look at it, there's only 1 out of the 4. So technically, I know the answer should be a quarter. Now, that's understanding what conditional probability is. If you didn't understand that, then I already gave you the formula for the conditional probability, which is PR of A, so chances of A happening, given that B has already occurred, is equal to the probability of A and B occurring at the same time. So what's the chances of both of them happening? And then out of the probability of B, what's the chances of B occurring first? That's the formula I gave to you. Now, if you were to answer this without using logic the way I just did, okay, let's prove that it actually equals to a quarter. So what we need to find is probability of A intersection B first, and then probability of B. Now, probability of B is pretty easy because, you know, what's the chance of getting B? Well, you got 3, 4, 5, 6. There's 4 numbers there that you're looking for out of a total of 6. So probability of B, we already know it is 4 out of 6 chances. True? Okay, whereas the other one, we're trying to find probability of A intersection B. So the first question is, what is in A that is in common with B? And we can both see that what's in A and is in B is just the number 6. So I can say there's only one item that is in common with A and B, 1 out of the total number of elements we have, which is 6. So we say it's 1 out of 6. Okay, so if I were to put it in, I would actually say chances of getting A and B would be 1 out of 6, out of the chances of getting B, which we already know was 4 out of 6. Now, for those who don't like fraction on fraction, you can actually just read it out first. It says 1 6, which is that. This massive line here means divide, and then you got 4 6. So there we go, we've got 4 6, and going back to primary school maths, how to divide fractions, we do the reciprocal. So that becomes now 6 on 4 multiplied 2. So this is 1 on 6 multiplied to 6 on 4. And you can see that 6 divided by 6 cancels out of 1. And you end up with a quarter. Okay, so you can see that the formula works if you follow through this. But that's what I'm saying. You don't have to do the formula because logically it made sense. And, you know, like you already had the event happening. Remember, it's a condition. It's a dependency. So the chance of you getting a 6 depends on what happened with B. And in our case, we already know that B was already greater than 2. So the numbers that are greater than 2, it can't be 1 and it can't be 2. So the sample space, or the possible outcomes you have, becomes 4 rather than 6. So from 6 possible outcomes, it reduces down to 4. And out of those 4, what's the chances of getting A? That's what conditional probability is about. So try to keep that in mind. Always trying to think about how do I get, like, what's the condition that happened first? Okay, get that around your head, then you don't have to memorize this rule and go through all these steps to get the answer. Okay, all right, let's try a second one now. I had question 4 on the list, so let's have a look. In Sam's class, 12 students play violin, 12 play piano, and 7 play both. Now, as soon as I see this, I normally think of cardinal maps, or in this case, they already tell you to do Venn diagram. I like to do cardinal maps just because cardinal maps is a Venn diagram, is just easier to see. Okay, it's up to you. I'm going to do both just so you can see how I do both, you know, either Venn diagram or cardinal maps. Again, if you're struggling with Venn diagrams, that was exercise, the one before, so that's 9D and E. Okay, so E and D are sort of to do with cardinal maps and Venn diagrams. You got to work on that before you get to F, which is what conditional probability is. Okay, so let's have a look. We got most times when you're drawing a Venn diagram, most of the time you have 2 events. So in our case, what I can already see is we've got 12 students play violin. So violin is the first event. Number of people who play violin, and number of people who play piano. Okay, so I will put P for piano, P dash for not playing piano, and V for playing violin, and V dash, or V prime, or V complement to mean that I'm not playing violin. Now they already say that Sam's class, 12 students play violin. So I know in total, 12 play violin. I know in total, 12 play piano. Now, you remember piano, the final sum is down here. That's your 12. Okay. And 7 play both. So that means this is in this square right here, this represents playing violin and piano together. And I know there's 7. Now, the question is, I guess we don't know the total number of students there are. Do we? It doesn't actually say, actually. Draw a Venn diagram. Use it to find the probability the randomly chosen student plays the violin, given that they play the piano. I would have thought they would have told you the total, but they haven't. So I guess we'll just fill out what we know. So in this case here, we know the number of students. I'm going to do it in red so you can see. We know that number of students who don't play piano but does play violin would be, that would have to be 5 there. 7 plus 5 gives you 12. And similarly, number of students who play piano but don't play violin has to also be 5 there. Which isn't really helpful because, I mean, I won't know how many students don't play piano and how many students don't play violin if they don't tell me the total. So if I were to draw a Venn diagram, it looks as if what's in common between the two, let's say this is piano, this is violin, well, I already know V intersection P is the center here, and that's 7. And obviously people who play piano and not violin, so playing piano but not violin, which is this region here, that tells me 5, and that represents here playing piano, but you see I'm not shading in violin, so this region here has to be 5. So I'm just going to put in 5 there. So they asked me to draw a Venn diagram. I got 5 there, and I also know a number of people who play violin but not piano is 5 there, which makes sense. 5 plus 7 for this circle here gives you 12, and if you look at the V circle, 7 plus 5 is also 12, and that fits in with what I have. Yeah, that tells me the total of but now anyways, we've got to answer the question. It says find the probability that a randomly chosen student plays the violin given that they played the piano. So in this case here, because we already know they already played the piano, okay, so I'm going to write it down. It's probability of, we're trying to find a student that plays the violin. So plays the violin. What's the chance of you playing violin if you already play the piano? This is a given probability. Now you can do the formula again, or you can do it logically. Now logically, how many people play piano already? We only got 12. Out of these 12, how many people play violin? Well, right there. It tells me 7. So logically, I would say the answer has to be 7 out of 12. Okay, but let's say you couldn't sort of see that and you wanted to use a formula, then alternatively you could use the formula is V given P is equal to probability of V and P occurring. So playing violin and playing piano divided by the probability of playing piano. But you quickly pick up the issue here is you can't find the probability of V and P because you only know it's 7 out of, and you don't know what the total is. Okay, and you can call that X if you want. It still works out. I mean, this might confuse you by saying this, but I want to say there are X total amount of people overall in this class. We don't know how many. So the chances are 7 out of X students are playing violin and piano. And then you have a look at that's divided by probability of playing piano, which we have 12 people in total out of 12. So you would say 12 out of X there. Okay, and you could do that, and that would just be 7 over X divided by 12 on X, but we know that when we're dividing fractions, it becomes times X on 12, and X divided by X cancels out, and you still get 7 out of 12. Same answer as I did up here. But obviously, I'm hoping that you didn't have to go through these algebraic steps to get the same answer because it's a logical question. Okay, so given what's already occurred, out of that, what are the chances of getting what you want? That's what conditional probability is. Okay, so hopefully you're starting to pick up the pattern. Let's have a look at question 5. Same drill. 2 dice are rolled and the outcomes observed. Okay, so I got two dice that are rolled. So I got 1 to 6 and 1 to 6. Those are the possibilities. Given that the dice both show the same number, okay, so given that they both show the same number, what is the probability that it's a double 6? Okay, well, right now, you got to think about what are you looking for? So you want to, what is the probability that it's a double 6? So that's what you're looking for. You're looking for probability of getting a double 6, okay? Given that, now it says, given that the dice both show the same number. So chances of already getting doubles is pretty much what it's saying. Okay, so chances of getting doubles, well, when you're rolling a dice, normally you can get, I'm going to draw a table, a lattice diagram so you can see. You can either get 1, 2, 3, 4, 5, or 6 on your first go. And let's say your second go again, you get 1, 2, 3, 4, 5, or 6. So there's a total of 36 possibilities here. You can get 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, and it carries on, right? There's like 2, 1, 2, 2. These are all the possibilities. On your first go, you might have got a 2, and on your second go, you might get a 1. But that's not what you're interested in. You see, what you're interested in is getting doubles, because it said, given that the dice both show the same number, meaning that you already got a double. You just don't know which double you have. You can either have 1, 1, 2 and a 2, 3 and a 3, 4 and a 4, 5 and a 5, or a 6 and a 6. True? Those are the only options. We're disregarding any other possibility because I already told you that it's given that you already have this. The condition is you already got a double. Now, out of all the doubles that you have, you got 1, 1, 2, 2, 3, 3, 4, 4, 5, 5. This is the only possibilities that you've got because they already told you it's one of these. And out of those, they're asking, what's the chances of getting a double 6? Which you can see that there's only 1, 2, 3, 4, 5, 6 options in total. But out of those 6 options, to get a double 6, there's only one. There's only one of them. So your answer for this question on a logical basis is 1 out of 6. Because there's only one double 6 that you're looking for out of all the possible doubles that you can only have. Okay, and that's what conditional probability is. Whereas if I didn't tell you that there was a doubles there, then like if I didn't tell you that you already had a double, then the chances of you getting a 6 out of 6, 6, 6 would have been 6. Sorry, it would have been one possibility out of a total of 36 because you don't know what possibilities you could get. So you don't narrow down the sample space or the possibilities. Okay, so that's what conditional probability does. The chances of getting a double 6 now is dependent on the new condition, and the new condition is you got a double. That's what you know. I already got a double. What's the chance of getting a double 6? That's what I'm looking for. So this is my already doubles. These are my doubles. And out of those doubles, what's the chance of getting my double 6? And there's only one out of the 6 there. Okay. Let's try the next one. Same drill. In Annabelle's class, 17 students own an iPhone. Okay. 7 own an iPad, and 4 own both. So again, same idea. In this case here, they didn't tell me the total number of students, so I might as well just use a Venn diagram in this case. You got an iPhone, so iPhone, and you got an iPad. Okay, you got an iPad, and they tell me that 17 students own an iPhone, 7 own an iPad, and 4 own both. So I always start off with the both because it's easier to see in the Venn diagram. Now, if 4 own both, but we said that 17 students own an iPhone, so in this circle of iPhone, it should all add up to 17. But if I already got 4 in this part of that region, then I only need an extra 13. So that would make sure that in the iPhone circle, this is the iPhone circle, that there's a total of 17, because that's what they said. There's 17 students who own an iPhone. You can, it didn't say that you can only own iPhone. It said iPhone. It didn't say I only exclusively own iPhone. So that's why this is 13, and that means on the other side, for you to have 7 to own iPad, this would have to be 3. 4 plus 3 gives you the circle for iPad, and we can see that, well, that's a total of 7 people that owns iPad, and it fits the story. Okay, so now I've got an illustration of what I have. The question is, what is the probability that a student owns an iPad given that they own an iPhone? Okay, so again, think about what the question's asking. A, probability, so chance of you getting an iPad given, it's always key, so there's a now condition. Given that you already own an iPhone, so you already have an iPhone. So that means the question is, how many people have an iPhone already? Okay, how many people already have an iPhone? Well, in total, there are 17 people who have an iPhone. There are 17 people who already have an iPhone. Out of those 17 people, how many of those have an iPad? That's what you're really asking. And you can see that the total number of people who have an iPhone, there's 17 of them. Out of those 17, how many of them have an iPad? Well, if you look at the region, clearly the only iPad region is here. That's 4. So we know that there has to be 4 people out of the 17 who have an iPad. Okay? Otherwise, what normally would have happened is you would have said chances of getting iPad only. If I just went probability of finding iPad, it would have been total number of people who own iPad would have been 7 out of, whatever the total number of students there are, which we don't know. They didn't tell us. And it would have been 7 out of whatever it is. But in our case, we're not just looking for iPad only. We're saying iPad, but you already got an iPhone. You already have an iPhone. So there's 17 people who already have an iPhone. Have an iPhone. And out of those 17 people, how many of them, what's the chance of getting an iPad? Then these people have an iPhone, but they don't have an iPad. But 4 of them will have an iPad. So the chances are 4 out of the total 17. That's why it's 4 out of 17. Okay. All right. Hopefully you're starting to sort of pick up the idea of what conditional probability does. It changes the chances because your total varies. Instead of the total outcomes, your total outcomes now dependent on whatever the event B is. All right. Or the first event, if you want to think about it that way. Now let's do question 9. I'm going to need a bit of space here. Now they've got a table for me, so that's pretty cool. It says, the following data was derived from accident records on a highway noted for its above average accident rate. So you either have fatal, non-fatal. They already add the totals for you. It's either because of speed, alcohol, reckless driving, other. Okay. And what I can see is there's a total number of 568 people who are in this record or survey or study. Okay. Now use the table to estimate the probability that speed is the cause of the accident. Okay, so in this case, I just want to know speed. How many people speed? Whether it's fatal or non-fatal, I don't care. Total people that speed is 130. 130 of them speed out of, well, how many people in total in this survey? Well, I've got 568. So the first answer, A, would have to be 130 out of your total, which is 568. Okay, because I'm saying probability of speeding. That's all I want to know. Chances of getting speed. Well, total number of people, there's 568 of them. Out of them, how many of those people speed? 130. Okay. Part B. It says the probability that accident is fatal. Well, fatal, this is under the category of fatal. 42 was fatal for speed, 61 was fatal for alcohol, 22 was for reckless driving, and other was 12. They're all fatals there, and a total of 137. So in total, I've got 137 people that are in a fatal accident. And so when we're talking about chances as well, okay, so there's 137 that are fatal, but out of what's the total number of people overall? That's 568. So that's why probability fatal is 137 out of 568, because that's the total number of people without any conditions. I'm just asking what's the chances of being fatal. So it's 137 out of 568. Now let's go to C. C says to find the probability that the accident is fatal given that speed is the cause. So now this is a different question, you see. This one is asking chances of fatal, okay? But if you already know, so given that it was caused because of speed. So you already know that it was because of the speed. So what you're really looking for right now is, it's not out of 568 people anymore, because not all people is in an accident because of speed. How many people are actually in an accident because of speed? There's only 130 of them. So it's not out of 568, it's out of 130 people who speed, because you already know they speed. Out of those people who speed, what's the chance of that being fatal is what you're really asking. Okay, so that's what it means when they say find the probability that the accident is fatal. So that's what you're looking for, given that this has already occurred. Speed is the cause. Okay, so out of 130 people who speed, how many people of those are in a fatal accident? There's only 42. That's why you'd say 42 out of the 130. Okay, see what I'm doing there? I'm changing the total number of outcomes. There was 568 before, but now it's 130, because I know that this group of people that are going to be fatal, I already know that they speed. So that's all I'm looking for. I'm just going to look at the people who speed, and out of those people, how many of those are in a fatal accident? That's what I'm looking for. Okay, same drill with, let's say, D. So when I do D, D is the same thing. Find the probability that the accident is fatal, again, given that the alcohol was the cause. So in this case here, chances of finding fatal or being fatal, given that it was because of alcohol. So out of the 568 people, not all of them are in an accident because of alcohol. There's speed, there's reckless, but I just want alcohol. So the total number of people who are in alcohol accidents is only 246. So the question is, out of those 246, how many of them are in a fatal one, which is 61? So you say 61 out of the 246. That's how the conditional probability affects the chances. Okay, so see how it's different when I ask, what's the chances of it being fatal? Well, you just look at fatal as 137 out of everyone. But when I tell you that it's given because of alcohol, well, then you got to look at the group of people that are in an accident because of alcohol, and then what's the chances of them being in a fatal? That's essentially what you're doing. Okay, so I've just done question 9 there. As you can see how I'm going through them, none of these are really hard, but exercise 9F is the most important for you to understand to eventually do question 15 and 16, which is what I left last to do. Yeah. Now I've already gone, what, 1, 2, 3, 4, 5 questions, and you got another 5. I'm already halfway. Okay. So really, it's just a bit of practice. Do the worksheet I gave you. Solutions are up as well. Do check them, read them, and that's all you need for the exam. Get yourself ready for the exam. Yeah, I'm just trying to get you an idea how to do these questions, the different scenarios that you might get. They're all relevant to your exam. Okay, so let's try this one. Question 10 is a bit different. So question 10 now, I would probably use a cardinal map just to sort of visualize it, or tree diagram if you prefer as well. That helps. Now it says, given that for two events, A and B, probability of A is 0.6. So I now know, okay, chances of getting A is 0.6. Chances of B is 0.3. Now they're asking me to find the probability, no, they said the probability of B given A is equal to 0.1. Now this is key. This is key because I gave you a formula. Remember, the one I gave you was probability of A given that B had occurred was equal to the chances of A intersection B, but here's the important part. It's over whatever happened first. So it's probability of B. Okay, that's for A given B. So if you switch the formula around, if you say probability of B given A, it'll still be chances of B and A occurring. That's still the same thing. B intersection A or A intersection B is the same thing. But the difference here is now it's out of the chances of A, because that's what happened first. Out of the group of people who are in A, what's the chance of getting B and A together? Okay, that's the difference. So if I were to answer this question now, I've got probability of B given A is equal to the probability of B intersection A out of probability of A, not B, so A, because A was the first thing that occurred. Now the nice thing is I already know B given A was 0.1, yeah? Because that's what they told me. They said it's equal to 0.1. So this here equals to 0.1, and then they told me PR of A equals 0.6, so this is equal to 0.6. So if I write it out, I would have 0.1 equals probability of B intersection A, which I don't know what it is, out of 0.6. Now, it just so happens that the first part of the question says, find probability of A intersection B. Now, probability of A intersection B is the same thing as saying probability of B intersection A. It's just saying, when do they both occur? Well, it's either A and B or B and A, same thing. Yeah, getting a 1 and a 2 or 2 and a 1 is the same thing. So, what I'm actually looking for right now, and I can rearrange this formula. See, it's a fraction. Now remember, this means PR of B intersection A. This is what I want. Up here is what I want. Now this is divided by 0.6. So the opposite of dividing, to remove the 0.6, we don't like fractions, remember? And I said if you don't like fractions, remove it by doing the inverse operation. Now if that's divided by 0.6, times by 0.6 on both sides. Okay, 0.6 divided by 0.6 will cancel out, and you're left with PR of B intersection A is equal to 0.6 times 0.1. Okay, and that really just gives you, what's that, 6, that's 6 out of 10 times 1 out of 10. That really is 6 out of 100, which is really 0.06. Okay, probability of B intersection A. That's what it equals to. So that tells me that for the first part, that's just 0.06. Okay, that's all I'm doing. So all I did was just, I know we don't like fractions, but like I said, every time you see a fraction, remove the denominator by multiplying whatever's in the denominator. Now we did that for truncus and rectangular hyperbolas. It's the same drill. Okay, same algebra. All right, next one is B. It tells me to find the probability of A given B. Now, same thing, probability of A given B. So B is the first event. Given that B had already occurred, it only changes the formula in this sense. It's probability of A intersection B over the chances of B occurring. That's the difference. See the difference between the two formulas? One's A is the denominator. Over here, B is in the denominator. And that's determined by what happens first. Okay, in our case, it's B. So if you were to answer this question, well, we just found out what A intersection B is. It's 0.06 divided by probability of B. They already gave us. They told us it's 0.3. So really, that's the same thing as saying 6 out of 30, which is the same thing as 1 out of 5. Okay, or you can change that to 0.2. All right. And that's question 10. So all I'm really doing there is I'm just manipulating the formula I gave to you in class for exercise 9F, and I told you to copy that down. Okay. Let's do another few other questions that also manipulate the formula. So let's have a look. For events A and B, question 11 says, if probability of A equals 0.7 and the intersection is 0.4, find the probability of B given A. So I'm going to do the same thing. Probability of B given A is equal to the chances of B and A occurring over whatever happened first. In our case was A, because it says given that A had occurred. So probability of A. Now, if I sort of put it all together, we already know what B intersection A is because they told us. They said it was 0.4. A intersection B or B intersection A is the same thing. So it's 0.4 divided by chances of getting A, 0.7. So your answer's 4 out of 7. Okay? Leave it as fractions. Don't change that to decimals. Wherever you can leave it as fractions, leave it as fractions. Sometimes you can change it to decimals, but in our case, 4 and 7 doesn't work out nicely as decimals, so leave it as 4 and 7. Okay, so that's part A. Let's do B. B says if A given B is 0.6, okay, so the A given B is 0.6, probability of B is 0.5, find the intersection. Now, same thing again. Probability of A given B, the only thing that changes is your formula. The formula now is probability of A intersection B, but because B is what it's occurred first, then it's out of probability of B. Okay? Now, they already told me that A given B was 0.6, so I know this is equal to 0.6. I don't know what probability of A intersection B is, but I do know probability of B, which is 0.5. So I'm going to write up here probability of A intersection B. And now very similar to question 10, you want to remove the denominator to find out what probability of A intersection B is. Well, then multiply whatever because that's divide. This means divide. Opposite of dividing is times. And instead of dividing by 0.5, I'm saying times by 0.5. And that cancels things out. Okay, so you times both sides by 0.5, balance in the equation. These two cancel out because 0.5 divided by 0.5 is 1. Probability of A intersection B is then equal to 0.5 times 0.6. 5 and 10, so that's 0.3 right there. Okay. But there you go. So that's B. Let's do C now. C, same drill. Hopefully you're starting to pick up the pattern. It's the same thing. You're just going to play around with the formula, yeah? So C, probability of A given B. Again, they tell you it's 0.44. And the formula for it would be probability of A intersection B over what's already happened first. In our case, it's B, so it's probability of B. A given B, they told us is 0.44, so I'm just going to write it down. This is 0.44 is equal to, and probability of A intersection B, they told us is 0.3, but what I don't know is probability of B, so I'm going to call that probability of B. Yeah, don't be afraid. It's the same drill again. So you don't know, you want to remove the denominator. We don't like fractions, right? We don't like fractions. It's okay. Do exactly what you just did for B, 11B in question 10. Same thing. This means divide by probability of B. True? So if you don't like it, times, do the opposite, times both sides by probability of B. See, that's fine. There's nothing wrong with that. You can do that. Probability of B divided by probability of B is going to cancel out to be 1. It's just how it is. It's like saying, if I add 3, so if I got $5 and I add 3 and then I subtract 3, well, you end up with $5 anyway. If I got $5 and I said times by 3 and then I divided by 3, you end up being the same thing. See, 5 times 3 is 15, 15 divided by 3, you end up at 5 again. 5 plus 3 is 8, 8 minus 3 is still back at 5. So it's the same thing if you divide by probability of B, so divide PRB and then times by PRB, it will just cancel out. Whatever 0.3 is. So 0.3 divided by probability of B is, and then times by probability of B, you're just undoing each other. That's why it cancels out, yeah? So when it cancels out, you're left with 0.3. On the left-hand side, I said probability of B multiplied to 0.44. Now, you see, you're trying to find probability of B, so you don't want times 0.44. How do you get rid of that? Same thing, do the inverse. Instead of timesing by 0.44, then I'll divide both sides by 0.44, and that now 0.44 divided by 0.44 cancels out to be 1, and you got PR of B is equal to 0.3 over 0.44, which I'd write it as 3 out of 44. Okay, and there you go. That's question 11. Let's go to our third last question, question 12. Okay, so you can see what I'm going through. I went through theory first. So most of the theory was logical. Most of these you could have done logically. So question 1, 4, 5, 6, 9 was all logical. Then we moved on to 10 and 11 and now 12 as well. We're manipulating the formula. Finally, when you get to 15, 16 onwards, and I prefer that you guys try other questions after 16 as well, they're all practicing to apply the conditional probability. Okay, so that's why I'm doing 2 examples over here, just so that you can see how I apply it and practice it. Then go through my worksheet and you should be more than ready for the exam. Okay, so let's have a look at this one. Question 12. In a random experiment, probability of A is equal to 0.5. Probability of B is 0.4. And now, this is a bit trickier. You've got union. A union B is equal to 0.7. Okay, now, you have to draw back on the first session on a Wednesday I taught you. I told you to copy this formula down. I said A union B was equal to chances of A plus chances of B minus the chances of A intersection B. So if you didn't copy it down that lesson, copy it down now. Okay, so this is called the addition rule. And most of the time, if you ever see a union B, it's likely you're going to use this formula. I promise you it'll be in the exam, okay? Every year there's always one. So copy this formula down. So here we go. We got this formula. They told us this is 0.7. So they told me this is equal to 0.7. That's great. Do I know what PRA is? Yes, I do. They tell me it's 0.5. plus PRB, yes, they told me it's 0.4. So my job is to find out probability of A intersection B, which, sure enough, it was the first question. Yeah, so A. Now, if I actually work this out, I don't know what minus probability of A intersection B is, right? I don't know what that is, true. But I can simplify this. This is what, 0.7. This becomes 0.5 plus 0.4 is 0.9 minus PR of A intersection B. Now, you can think about it logically. 0.9 take away what will give you 0.7. Obviously, it has to be 0.2. But let's say you didn't know that. We can use algebra. Okay, let's use algebra just in case you're not familiar with it. See, instead of minusing probability of A intersection B, I can say add probability of A intersection B. Why do I do that? Because minusing it and then adding it will cancel it out, true? But then if I add it on the right-hand side, I got to add it on the left-hand side. So plus probability of A intersection B. Okay, so now what do I have left? I've got 0.9 on my right-hand side. I've got probability of A intersection B, and that's plus 0.7 there. Okay, because that's a positive 0.7 and that's plus. So now my goal is to find out probability of A intersection B, but I need to remove plus 0.7. So if instead of adding 0.7, I can say minus 0.7. Minus 0.7. See what I'm doing? 0.7 minus 0.7 cancels out to be 0. 0.9 minus 0.7 gives you 0.2, like I said. So probability of A intersection B is equal to 0.2. And we could have done that logically before. We could have said 0.9 minus something equals to 0.7. We already knew it was 0.2. Okay? But you see, what I did was I just used the formula that, I think this was exercise 9C, if not 9D. But it was the first slide on Venn diagrams that I showed you. Okay? But there you go. So now I know the first question for part A was equal to PR of A intersection B is equal to 0.2. Now let's have a look at B. B tells me to find probability of A given B. So hopefully if you're watching this video, you're very familiar with the formula now. So probability of A given B is the same thing as saying probability of A intersection B given or over the chances of B, because that's what's happened first, right? Now, looking at all the pieces of information, they've given me A union B. I figured out I want to find A given B. To find A given B, I need A intersection B, and I need probability of B, which conveniently in part A, I already found A intersection B to be 0.2, and they already told me what probability of B is, which is 0.4, so that's what, 2 out of 4, which is the same thing as saying half, which is the same thing as saying 0.5. Okay, let's go to C. Same drill, it's now saying probability of B given that A had occurred first. So the only thing that changes in your formula, A intersection, also I normally like to write it like this, B intersection A, doesn't really matter, divided by chances of getting A. Now, A intersection B and B intersection A would be the same thing, so we say it's 0.2 out of chances of A, which they told us before was 0.5. Okay, so there's that a 0.5, and my answer is 2 out of 5, or you can write it as, what's that, 0.2, 0.4. Okay, there you go. That was, but you can see all I'm doing is just manipulating the formula. You only got this one that I gave you on the last session for 9F. We had a double session on that. And then this is on the Wednesday as well, addition rule. Okay, so keep in mind, just copy those two formulas. You do need that. 9G, if you know, the last 5 minutes I gave you another formula as well, whether you copied it or not, just in case you didn't, and you're doing 9G, you need independent events. So anytime they mention about independent events, you just need to show chances of A times chances of B is equal to chances of A intersection B. And that's your pretty much all your formulas you need for probability. Okay? But that's for another video. So I'm going to rub this off. All right, so we've done manipulation of the formula. We've done logical answering of conditional probability. Now we've got to apply. Okay, so let's do 15. Question 15, here we go. I normally like to draw this using a tree diagram. It's up to you how you want to do it, but I like the tree diagram. It's easier to sort of see what's going on. So here we go. We've got a current football fixture has the local team playing at home. So the other play at home. Actually, did I do this example in class? I don't know if I did. Let's do it again anyway. You either play at home for 60% of its matches. So in my head already, I'm like, all right, so I either play at home or I don't play at home. So H dash or H complement or H prime. Okay, so home and not home. 60% of the time I play at home, so that means 40% of the other times I don't play at home. When it plays at home, so it says when it plays at home, so there's a condition. When I do play at home, the team wins. Okay, so that's a condition. I have to play at home. So when I do play at home, the chances of me winning is 80% of the time. So I either win or I don't win. Or I don't play at home and I either win or I don't win. True? What they've just told me is that if I do play at home, the chances of me winning is 80%. So that means it's 0.8. So that means the chances of me losing is 20%. It's 0.2. Then they tell me the next line that says when it plays away. So that means I don't play at home. When I don't play at home, then the team only wins 40% of the time. So I only win 0.4 of the time, and this has to be 60% of the time I lose. Okay, so I've got my tree diagram here. What you need to understand is this last branch, okay, is actually, and a lot of students don't realize, yes, it was home, win, but it's win given that you played at home. It's not winning given that you played at home. This is winning given that you didn't play at home, and this is not winning given that you didn't play at home. That's technically what the tree diagram is. It's a conditional tree diagram. It's a dependent tree diagram. Unlike every other tree diagram you've done, like heads and tails, those are independent. Because when you flip a coin, it doesn't matter. H tails, H tails, H tails. It doesn't matter. If you got a H before, it's still going to be a half. But it does change the probability if it was a given. That's the difference between them. Okay? So now I've drawn my tree diagram. And I just need to answer the question now. It says, what percentage, so find the probability, of its games does the team play away and win? So I'm really saying find the chances of playing away, so not at home, and, so intersection, and win. That's what I want. So if you look at the branches here, the only way that could happen for me to win, so these are the wins, I win and I win, but out of those, which ones do I want? I want it to not be at home. So this is not at home, there's chances of me winning. Now the only way to get there, as you can see, it is a 40% chance of not playing at home, so 0.4. And so that means now I'm doing another 40% chance of winning, so it's of. So 40% of 40% is 0.4 times 0.4. That's the chances. That's what I'm doing. So I'm going this way to that way. So it's 0.4 multiplied to 0.4. Okay, and that gives me now what? That's 0.16. Okay, 16 out of 100. And that's the chances. 16% chance of you winning and playing away. Okay, so when you play away and for you to win, the chances are 16%. That's technically what you're doing. Or effectively, you're doing 40% of 40%. Because there was a 40% chance of winning, but you had to play at home, given that you played at home. But there's a 40% chance of you playing at home anyway. I mean, away from home. So 40% chance of 40% chance gives you 16% chance. Okay? Or another way of thinking about it is 50% of 40% is 20%. True? But then 40% of 40%, we got ourselves as 16%. Makes sense. It has to be lower than 20. Yeah? But that's what I've just done. I've just answered the question using a tree diagram there. Let's try another one. 16. You can try 17, 18 if you like, or go beyond. But this should give you a pretty good idea of how to do conditional probability. So let's have a look at this one. It says, the probability that a car will need an oil change is 15%. So you either have an oil change, I'm going to do O for oil change, or you don't have an oil change, right? And there was a 15% chance, so 0.15, and that would mean that I would have to have 85% chance. So 15% chance of oil changing, 85% of not oil changing. Now they say the probability that it needs a new oil filter is 0.08. Okay? Just be careful here because they didn't say that the oil filter is dependent on the oil change. So I'm just going to stop there for a moment and read the next few lines before I actually try to answer the question. It says, and the probability that both oil and the filter need changing is 0.003. All right, in this case, you know what I'm going to do? I'll do a cardinal maps because they gave me an and question. They gave me two chances of two things occurring at the same time. So I'm going to use a cardinal map to illustrate what's going on here. I've got either I have an oil change or I don't have an oil change. Now they told me the chances of getting an oil change was 15%, so that's 0.15. I know it has to be 100% in total, so this is 0.85 there. They told me that the chance of you getting a new filter, so F for filter and F dash for not getting a filter, they said it's 0.08. So chances of getting a new filter is 0.08, and chance of not getting a filter then would have to be 0.92. So 92% chance of not getting it, and 8% of getting it. Then they gave me that last part, which is key. That's why I'm using a cardinal map to visualize it. They said the probability that both getting an oil and a filter need changing is 3%. So this is 0.03. Now, if that's 0.03, you can fill out the table now. You can say, all right, well, this has to be 0.05 because 3% plus 5% gives 8%. This has to be 0.12 because 12% plus 3% is 15%. And finally, 12% plus what to give you 0.9, this has to be 80%. Which makes sense again, because if you add vertically, 0.05 plus 0.8 gives you 0.85. So I've got my table. Now, what's the question? The question says, given that the oil has to be changed, so you already know that oil has to be changed. Okay, so this is the condition. Oil has to be changed already. So remember, this represents oil needs to be changed, and that's 15% of the people already. Okay, so already out of those 0.15, what is the chances that you need a new oil filter? Which is 0.03. Okay, so out of those people who already need an oil change, which is just 0.05, oops, 0.03, how many people of those group here, so out of these people, how many of those need a filter change? So I'm using logic right now. That's just 0.03 out of 0.15 is what I'm doing. Alternatively, again, you can write it out. You can say probability of needing a filter change given that you need an oil change is really what it's asking. And you could do this by saying probability of F getting a filter change and getting an oil change over the chances of getting, chances of getting an oil change already. Yeah, you can use that formula if you wanted to. So it's kind of like F given O equals to F intersection O over chances of O. And if you followed that, you can still answer the question and it still be 0.03 out of 0.15. I'd still be correct. And I'll show you. So F intersection O, you would say that's 3% because that's 0.03 out of 1. So it's really 0.03 out of 1. That's the chance of you getting F intersection O divided by probability of O. Now, probability of O, we already got over here is 0.05. So it's 0.15 out of 1 again, because that's the total percentage. Now, if you write that out, that's 0.03 out of 1 divided by 0.15 out of 1. I know a lot of us don't like fractions, but hey, it's something you just got to get used to, yeah? 0.03 over 1, and when you're dividing, do the reciprocal. That becomes times 1 over 0.15, and you can see 0.03 times 1 is 0.03 over 0.15, which is exactly what I told you before without even doing all these calculations. It's pretty logical that it's 3 out of 15, and that's 1/5, which is 0.2. Okay? But that's what I'm saying. Like, you can look at it logically and say, well, if you already know you have an oil change, a filter change, then there's 15% of them that need an oil change, and out of those 15%, how many of those people need a filter change? And that's 3%. So 3 out of the 15. Yeah. But that's the other algebra for it too. So hopefully, after doing all these examples here, you're going to feel a bit more confident. But those are the questions I set. I've done pretty much 10 questions with you there for exercise 9F. And hopefully you can see it's not really that hard. Probability is very easy to do. I do want you to practice other questions. I mean, if you feel confident, you don't need to do the others, but they're all pretty much the same drill. If you just went on and did, question 20, that's a nice set of questions there for you to try. Use a cardinal map. That could help as well. You can do question 21. That's a good way to look at it. So 20 and 21. Yeah, you can do that if you're tight on time. Do 20 and 21. If you have a lot of time, then I'd say just do the last few questions. So you can do 20, 21, 22. Don't bother with 24. You probably would have been done with that if you've done 20 and 21. Maybe you want to do 25. Otherwise, go and revise quadratics and cubics for your exam. And just speaking of exams and the resources, I'm just going to show you in the Year 11 folder. I told you that in the latest update, I told you that there's a a folder that I put with a link to the resources. This is the Google Drive resources, by the way. So when you click on the link, exam resources or links, okay, you click on that in that folder. I've given you a link to the Google Drive where all students should be able to access and get exam papers. Now, when you click on it, what will happen is it'll take you to a page and nothing will load, right? So it will say something like this. It's okay, click this link. It says Year 11 Methods Resources. If you just tap that, it will take you to the Google Drive. And in there, you can then access, either your methods exams or your specialist exams or general maths exams. But, if you go to your methods, once it loads, of course, you got your exams there. Go to your exams and you got Unit 1. And under Unit 1, you got 2015, 2016, 2017. I'd say, given that we've got short on time, go with 2017. That will give you a better idea of what we need to do. Yeah, because I'm doing 2017 on Tuesday. Okay, so if you want to have a look ahead and start on 2017. Otherwise, you can start in 2015. I do 2017 on Tuesday, and then you got 2016 to do, and you should be ready. You should be ready. Okay, so looking forward to it. Remember, it's cubics, quadratics, and all the functions, which you guys did really well on that. And I'm hoping that your cubics and quadratics now improve because you can read the graph. Okay, you know how to find A, read from an equation, find the equation, substitution, you can do all that. So hopefully your linear, your quadratic, cubic, and your functions are really good. Then the only thing you're left with is probability, which, like I said to you, it's really easy to pick up. Okay, so really focus back on quadratics and cubics. I think that's where I found most of you are still struggling, like with discriminants or inequalities. Application of that. That's what you want to do, and that's what these exams are for you to look at and try to focus on those questions. Practice factorizing, completing the square, solving for x-intercepts, sketching graphs. Better sketch the graphs correctly, in the exam. It's very important that you're sketching it correctly, otherwise you'll be losing marks. But there you go, and remember to use your CAS. Learn to use your CAS again. So brush up on it again, define, solve, graph, fix the windows, analyze the graphs, those kind of things, check your settings, those kind of things. Alright, thank you, and enjoy your long weekend. I'll see you on Tuesday.